Right, so this is version Z on Algebra, and it just covers the graphical representations. We've done this on the basis that there are an awful lot of graphical representations which make up effectively section A, and we could be asked about any of them. So, transformations. Transformations and inverses are something that we don't actually tend to do a lot of, but are still nevertheless on our syllabus. So, if we consider graph A on the data sheet, that's our pendulum. We're thinking about a transformation. Now, an inverse happens to be where we can swap the x and the y values over on our graph. So, at any point where it would have been a y value, it now becomes an x value. Where it would have been a y value becomes an x value. So what we have is a line, y equals x, and what we do to inverse is we reflect in that line. So what we're aiming for is a graph that looks, balance error, a lot like that. Not possibly the neatest thing in the world, but everything where it was on the x-axis, it's now the same distance on our y-axis. So the transformation that we've used to do that is a reflection in the line y equals x. Okay, so which one could be the inverse? So if we look at all of them, the one that looks most like our inverse is D. So this one's basically a quadratic graph. This one is the inverse, so that's a square root graph. So the graph that could be the inverse is graph D. So, period of a pendulum. So we know period, y seconds, length, x, and that's in meters, can be modelled by this function. And k is a constant. So a constant is a number. It doesn't change, and you will normally be asked to find it. And it will stay the same in your equation for the whole of that bit. So, value of k. Things that we know. We know that the period is 0.8 when the length is 2.56. So if we substitute these two things into this equation, we end up with 0.8 equals k square root of 2.56. So, calculator, if we divide both sides by this square root, what we'll end up with is 0.8 over square root of 2.56. And that happens to be 0.5. So k equals 0.5, and most of the time this question will then say, hence, find an equation or find a function of y in terms of x. So that means we'd have to substitute in our value of k into the equation. This is useful because, if nothing else, we need it in the next question. So, we are looking at the period when length is this. So, our length is x. So what we're going to do is we will substitute in finding y. We've got 0.5, and then our value of x at this time is 1.69. So 0.5 times square root 1.69 gives us a y value that is 0.65, and that is in seconds. Okay, now we're asked to find the length when the period is 0.6. So when we substitute that in, we've got our period is 0.6, and that equals 0.5 square root of x. Now we can do this by rearranging, so we can divide both sides by the 0.5, which will give us 0.6 divided by 0.5 is 1.2, and that equals the square root of x. So x will equal 1.2 squared, and that happens to equal 1.44. If you're not confident with rearranging, what we can do is we can stick this in a graph. So we've got y equals 0.5 square root of x, and so we are going to need to put a decent view window in there. If we try zoom auto to start off with, we hopefully get something useful, which very helpfully looks like the graph that we've actually got in part A. So if we know y, we can ask it to calculate x when y is 1.2. This doesn't mean it's wrong, it means it can't see it. So what we'll need to do is look at our view window, and our maximum x currently is 0.006. So it just can't see it. Our maximum y is 0.038, so it can't find 0.6 if it doesn't go up that high. So if we go for a y value of 5 and an x value of 2, then we can go gsolve xcal y equals 0.6, and then it will quite happily tell us what it is. Because it's now on the screen, it can actually see it. Okay, so moving on, we are now considering graph B. So first off, we're asked to sketch the graph of the inverse of B. So the inverse of B, what we can look at is the fact that we've got this value here. We're not given any letters here. So if we call this A, then when we do the inverse, A is going to have to be the same distance in the other direction. And then what we'll do is, because we're doing it in y equals x, that's a 45-degree angle, which is basically there. So we're going to reflect it in this line. So when we draw a sketch of the inverse, it's going to go up, meet at the point, and then start going away again. You need to make sure you mark on any points that are of interest. So the fact that this value and this value are the same. You need to show that if it's touched this line here, that this one also touches it in the same place. You either need to basically number things or show really obviously what's happening. Okay, so number of bacteria is y. So bacteria is y, time in hours, and we have a function. initial number of bacteria. This is state. State basically means you don't need to do working out. You can just look at it. So things we might want to know is if x equals 0, if anything to the power of 0 is 1. So our initial thing when x equals 0 is going to be y, our number of bacteria, is 240. How long is time? So we're going to be working out time, and we want bacteria to double. So there's a couple of different ways of doing this. Probably the easiest is to go, well, we start off with this many bacteria, and double that is 480 bacteria. So what we want to know is 240 e to the power of 0.2x. So we've just substituted into our equation double the number of bacteria. So if we divide both sides by the 240, we end up with 2 equals e to the power of 0.2x. And this is where our log laws come in. So if we ln both sides, we end up with ln 2 equals ln e 0.2x. Now, hopefully we know that ln and e cancel. So we then end up with ln 2 equals 0.2x. And then by rearranging that, we've got a fraction of ln 2 over 0.2. So x should hopefully equal 3.466. So that equals 3.47 to 3 significant figures. And that's in hours. So in theory, they could ask us for hours and minutes. And at that point, to work out minutes, if we take away the 3 hours, we're left with this many. And we can divide that by 100 and times it by 60, which gives us basically 30 minutes. So we've got 3 hours and 28 minutes. Okay, so the graph of ln y is plotted again at x, and we are asked to state the gradient. So, very similar to what we did over here. We've got y equals 240 e to the 0.2x. So if we ln both sides, we end up with, that is not legible. We end up with ln, so we are learning both sides, so we end up with ln y equals ln 240 e0. So next bit that we're after, we can separate this bit. So when we separate using ln, we end up with ln 240 plus ln e 0.2x. Now, you may know that ln and e cancel and want to go straight for this bit, but it's probably worth the safety of writing it in because it'll only take you a second or two. So 0.2x. So if we're looking at this as a y equals mx plus c equation, we've got this on our y-axis we've got this on our x-axis, which means the thing we're timesing by the x has got to be m, and the thing that's a number on its own, not with the x, is going to have to be c. So, if we're plotting the graph of ln y against x, we are plotting this graph. So, the y and the gradient of this graph is the 0.2, and the y-intercept is going to be ln 240. So the gradient of the graph is going to tell us how quickly it's changing. It's doing a rate of change. So ln 240, they may well want us to actually work out for them, and that is going to come in at 5.48. Right, graph C on the datasheet, gravitational force, inversely proportional. Now, inversely proportional, as you will have done in GCSE, actually means that Y, our gravitational force, is proportional, so it's equal to K, which is just a constant, so a number, and it's the square of the distance. So if we call our distance x, what we end up with is an equation that is y equals k over x squared. We're then just given some information. So we have 4 meters apart, gravitational force. So gravitational force when they are 8 meters apart. So there is a very cunning thing that you can do of noticing that this is twice as big. So x squared, so x should be twice as big. So we'd then square it, which would give us a quarter. However, given in an exam, spotting very subtle links can be really hard. There's the other way of doing it, which is to substitute in. So we've got our gravitational force, which is y. So we have 1.4 times 10 to the power of minus 18. And that is equal to k over 4 meters squared. So this means that k is going to be 4 squared times 1.4 times 10 to the 8. So we've got 1.4 times 10 to the 8 minus 8. Then we'll times that by 4 squared, which will be 16. And what we end up with is that k is 2.24 times 10 to the minus 7. So, if we can find the gravitational force when they are 8 meters apart, we know that y is our gravitational force. We know that k is 2.24 times 10 to the power of minus 7. And we've got 8 meters apart, so that'll be 8 squared. So, if we take that and divide it by 8 squared, what we end up with is 3.5 times 10 to the power of minus 9. Seems absolutely tiny, but then the example we were given was to the minus 8, so actually it's kind of okay. We're then asked to find an equation for y in terms of x. In reality, that's kind of what we did up here. So we'd find k like this and then write our equation as y equals 2.24 times 10 to the power of minus 7 over x squared. Hence, find the distance when the gravitational force, so this is y, so gravitational force is this. So we've got a gravitational force that is 2 times 10 to the minus 16. We know that K is 2.24 times 10 to the minus 7. And we know that that's over x squared. So we could put this into our calculator and do xcal, or we can rearrange it. So at that point, x squared is going to be, if we swap these two, we end up with 2.24 times 10 to the power of minus 7, and we'll divide that by 2 times 10 to the power of minus 16. So we end up with something giant, and that is 2, 4, 6, 7. So we want to then square root that. Now, normally you would get a square root which would have a positive and a negative answer. However, you can't have a negative distance away from something because it would just be the positive distance on the other side. Normally, we would then want this to 3 significant figures, so at that point it would be 3, 3, 5. Right, so graph D. This is a quadratic graph, and what we're told is it's the distance fallen in meters in terms of time, and we're using seconds, and it's modelled by this equation. So, rearranging to make x the subject. We've started off with this equation, so we can then divide by this 4.9. So we've got y over 4.9 equals x squared. And then from there, we can square root both sides. So we'll end up with y over 4.9 equals x. Okay, find the time it takes to fall. So find time, fall meters. So we can substitute in our meters. So we get 98. And we want to find the time, which is x. So we can do 98 over 4.9, square root it, and that should give us a value of x. So what we've got is the square root that over 4.9, which is 2 root 5, which is 4.47 seconds, and that's to 3 significant figures. And that is really quite ridiculously fast, but we'll go with it. So, part C. Find the equation of the graph when it is translated by this. So, really sneaky way of doing it, and I must admit, not ever seen it written this way before, but what we have is this is your translation in x, this is your translation in y. And this is a movement, so it's adding something on. So we have y equals 4.9. Then the x value is going to have to go in with the x, was plus becomes minus. Y value stays the same and just gets added on outside of the brackets. So x value does the opposite of what you expect. So was plus, now minus. Goes in with the brackets because it's x, and y comes outside. So express this in the form y equals ax squared plus bx plus c. This is going to mean that we are going to have to... that goes squared there. We're going to have to expand it. So, depending on how confident you are with this, if we use the box method to expand this, we've got x and minus 2, x and minus 2, which will give us x squared minus 2x minus 2x and plus 4. So we go to y equals 4.9, and then we've got our x squared. We can combine these. One of my GCSE students refers to this as the peanut method because it looks like a peanut in its shell. So minus 4x plus 4, and then we've got the plus 5 on the end. So we can multiply this through, so we end up with y equals 4.9 x squared minus, then we're going to need 4 lots of 4.9, so 19.6 x. Then we actually need this again for working out this, and we've got to add on the 5 to it as well. So we end up at 24.6. This bit is actually quite useful because quite often they ask us to put in a value of y and then rearrange it so it becomes 0 equals. So it's done in exactly the same way, only changing the side of the y, so changing the sign as well. Okay, so graph E, taxi company charges a flat rate of this much and a rate per mile. So what this is actually going to give us is a value of our intercept of £4.50 because that's our starting cost, and a gradient of £1.20 because we increase by £1.20 each mile. So the equation is going to look like y equals 1.20 x plus 4.50. Now, because it's money, it's kind of not a problem if you leave the zeros in. However, from a maths point of view, you don't actually need either of the zeros. So we have an equation for our second company. So our second company doesn't start at £4.50. It starts quite a bit lower. Well, a bit lower at 4. So we start at £4, and then it increases a little bit faster. We've got a gradient that's a bit faster. So our first company, we have a gradient of 1.2. Our second company, we've got a gradient of 1.4. So that one was starting at £4. So if you're going only a short distance, so this bit, what we find is the pink one is lower. But once we hit this point, we can see that the black one is lower. So we're asked, up to what distance is the second company cheaper? So what we can do is, if we put that into our graphs, we've got a first one of 1.2x plus 4.5. We've got our second one at 1.4x plus 4. And if we zoom auto, it may well give us something nice. It gives us something nice. And what we can see is starting at different heights and crosses about here. So G-solve, intersect, that will tell us exactly where it crosses. So these two cross when x is 2.5 and y equals 7.5. So what this tells us is up to 2.5 miles A is up to 2.5 miles B. So this company we're going to call B because it's in part B of the question. This one we'll call A because it's in part A of the question. So up to 2.5 miles, B is cheaper at 2.5 miles. Both cost £7.50 and after 2.5 miles, A is cheaper, and that's because it goes up by less each additional mile. Graph F on the datasheet is a Lund graph. It's the inverse of an exponential graph, which goes the other way. So, information that we are told. Loudness is measured in decibels, a thing we actually use in the sine curves a little bit later on. And in terms of intensity, X is measured in W over meters squared. So it's kind of about how it spreads out with distance. So this is modelled by this equation. So learn X over X naught. And X naught is the sound intensity at threshold of hearing. So that bit where you can first hear it. So first off, we want to find the loudness when its sound intensity is at the threshold of hearing. So what that's asking us to do is find Y when X, our sound intensity, equals X naught. So if we put that into our equation, what we can do is go Y equals 4.343 ln brackets. Now X is at the threshold of hearing, so is in this case X naught. So that means that is X naught over X naught. So what we can do at that point is either put it into a calculator, or we know that X naught over X naught is going to be 1. So we can have 4.343 ln 1. And that happens to equal 0. So the loudness, when the sound intensity of 0, there is no loudness. It's the bit where you can only just hear it, or a tiny bit quieter than you can just hear. So Y at that point is going to equal 0. So find the loudness when X equals 100 X naught. So putting that into our equation, we have Y equals 4.343 ln brackets. Our x value is 100x naught over x naught. Now, x naught and x naught will cancel. So what we end up with is 43.343 ln 100. So that should give us a value of y equals 20, or 20.0 if we want three significant figures. Okay, so find to the nearest million the ratio of sound intensity to the sound intensity at the threshold of hearing when loudness is 80 decibels. So we want a ratio. So if we start off, we know that our loudness is 80. So we know that loudness is 80 means that our y value is now going to be 80. And so we've got that 80 equals 4343 ln brackets x naught. Now, we don't know how many times it is, so actually at the moment we'll just put it as A. So what we've got is, if we do it a bit bigger so that it's easier to read, is ln A x naught over x naught. So our x naughts can cancel. So we will have ln A. And if we take this moment to divide 80 by this, what we end up with is 80 over 43. And that is equal to ln A. So we have 18.420 equals ln A. So if we want to get rid of a ln, we are going to have to use E. So we've got E 18402 equals A. So that is 18.40. So that is 1, 2, 3, 3, 1, 9, 4, 8. That is a lot bigger. So it is that many times bigger. So we've been told to find it to the nearest million. So that is 1, 2, 3, 4, 5, 6. Now, if we round that up to the nearest million, what we end up with is 100 million. And now we're going to rearrange this to make x the subject. So, starting off, we've got this equation. So, if we deal with the number bit first, then what we end up with is y over 4.343 equals ln x over x naught. Then if we e both sides, we get e to the power of y over 4.343. So e and ln cancel, so we get x over x naught. We can then times both sides by x naught, so we'll have x naught e to the power of y over 4.343, and that equals x. Graph G. Number of items sold is y. the price is X, and we have an equation. So there are certain things that on a graph, if we're given that much of the equation, that we will know. We've got our y-intercept. So we've got that value at 2400 when that is 0, and we've got a minus 80. So the number of items is y. When the product is given away free is 0. So that gives us our intercept. Why is the model not valid for a price of £35? So that is going to be our value of X. So we would end up with y equals 2400 minus 80. And then when we substitute in, stick it in brackets so our calculator can cope better. We've got 2400 minus 80 brackets 35. And that comes out at y equals minus 400. So this can't be valid because you can't sell a negative number of things. So it's not going to be valid, as this implies a negative number of things sold. Okay, so find the gross revenue if this is £20. This is a slightly mean question. So revenue is not your profit, it's how much comes in. So that's your money received. So if it's 20 quid, we've got 20 is our value of X. So we've got our same equation. So we've got y equals 2400 minus 80. Only this time we've got £20. So the number of things sold is going to be, if we just go back in there and change that to 20, is going to be 800. So we have 800 things that have been sold. But our question doesn't ask us how many things have been sold. It asks us how much money do we receive. So if you sell 800 things at £20 each, the amount of money that you will make is £16,000. And that's it.